We are going to look at the shortest path problem for a connected edge-weighted graph G. And we're given a source vertex, that's a vertex U in the graph G, and we want to find the minimum weight of a path from that source vertex to every other vertex in the graph. And we're going to use alpha as the map, that is the weight function, which assigns a weight to every edge of the graph. The algorithm that we're going to look at is called Dijkstra's algorithm, and I've already written down all of the steps of the algorithm, and these are them. So the first step and the second step are basically the setup. So what we do is the very first piece of setup is to make a set S. And right now it's going to be set to the empty set, so there's nothing in S right now. But it will store all of the vertices of the graph for which a shortest path, or shortest weighted path, has been found. So this is really the set of all of the ones that we have a solution for. And I would like to point out that because we have a connected graph, at the end of this algorithm, the set S will actually contain all of the vertices of the graph because we can get to all of the vertices of the graph from our source vertex U. If it was a disconnected graph, or maybe we'll do another video with a directed case, then it's possible to have S not including every vertex of the graph. Alright, so the second step is to take a look at the vertices and start to apply labels. Now, what we want to do is have a labeling function, which I'm going to call T, and it's going to give the minimum weight of a path to that vertex from U that we know of so far. So what we know is that for the source vertex, to get from itself to itself, you don't have to travel any distance at all. So what we do is we label it with a T of U equal to 0. Now for every other vertex V, which is not the source vertex U, what we're going to do is set the label to infinity, just because right now we do not have any path yet that goes from U to V. So we'll just set it to this maximal value. And now the next part is we want to add the vertex U, which is the source vertex, into our solution set. Now that should be clear because there's certainly not going to be any path of weight smaller than 0, which was going to get us from U to U. So that we can just include right away into S. Now that we've done the setup, the most important step is step number 3, because step number 3 is the step that ends up getting repeated over and over again. So what it says is if W is the newest member of the set S. So let's think about that for a moment. Right now, if we've just done step 1 and step 2, then the newest member of the set S right now would be the vertex U. But in general, whatever was the latest vertex that was added to the set S is what we want to look at. So for this latest vertex, we're looking at all of its neighbors. So for every vertex that's in the neighborhood of this newest member, which is not already solved, what we do is we take a look at its label. And what this says is you want to reset the label to be the minimum of whatever its label was before and whatever the label of the last vertex was together with the edge from V to this last label. So basically we know that this exists because it's in the neighborhood of W, which means that there is an edge VW, and it is definitely weighted with some weight alpha of that edge VW. So what you do is you take the weight of the path of minimum weight that got us to W, and then we tack on the weight of the next edge that gets us to V. Now what we do is we look at those two pieces. So really there's this piece here, what it used to be, and this piece here. And we compare the two. And if this is smaller, we'll choose this. And if this is smaller, we'll choose this. So we're just taking the minimum. Now once we've done that for all of the neighbors of the vertex W, then we go through and we pick any vertex which is not yet in the solution, which has a minimum weight, a minimum label. And then we add that vertex to the set S. And we'll repeat step 3. So we go back up to here until we've completed the entire algorithm. Now, when this algorithm terminates, the solution is going to be given by these labels, T of V. So for every vertex which is in our solution set, then the label of that vertex is the minimum weight of a path in the graph with that given weight function, from the source vertex U to that particular vertex V. So really, it's just reminding us that this set S is keeping track of the solutions, and these T of V labels are the actual minimal solutions. So what we're going to do now is we're going to take a look at an example, because when you read through the steps of an algorithm like this, it can be sort of difficult to see how it's actually working until you play with an example. So let's scroll down here, and here we have this example. So this pink graph is the graph G, and the vertices are A, B, C, D, E, F, and there is already a weight function on the edges, and that's given in the green right here. So what we're going to do is we're going to start off by saying that our source vertex is A. And what we're going to want to do is we're going to want to use Dijkstra's algorithm to go through this graph and figure out the paths of minimum weight from A to any other vertex. And in fact, you should be able to just look at this graph and find those numbers yourself. And that's actually a good way to double check, but what we want to do is run through the algorithm so that we could see how it would work in general. So step 1 is really just to set up the solution set, and it's got nothing in it right now. Okay, now step 2 is to take a look at our source vertex, and we're going to give it a label, so the label of the source vertex is 0. Whereas the labels for everything else is going to be set to infinity. So T of B and T of C, T of D, T of E, and T of F. And for now, the labels of all of the other vertices are set to infinity. So T of B is T of C, which is T of D, T of E, and finally T of F, and these all equal infinity. So that's the second step here we've initialized. And then what we want to do is we want to append the vertex A, which is the source, into our solution set. So what we're going to say is that S is now equal to the set A. Alright, so now we've initialized everything, and what we're going to do is look at step number 3. So I'm going to do step number 3 right here, and let's just go back up to remind us what step number 3 is. It says W is the newest member of the set S. So right now that newest member is the vertex A. What we do is we look at the neighborhood of the vertex A, and if it's a vertex in the neighborhood which is not yet in the solution set, we're going to try to figure out this. So maybe I will just take this little piece because it will be useful for us to remember. So I'll just copy that little piece. And I'll paste it down here, and I think some extra stuff can just go away like that. Okay, so this is the little piece that we're going to need to remember. So let's take a look at all of the vertices that are in the neighborhood of the latest member. What's the latest member? Well, it's the vertex A. It's right here, so let's take a look at the vertices in the neighborhood. Those are B, C, and D. And clearly none of those is in the set S yet. So what we want to do is we want to apply this little piece to each one of those. So what we're going to do is we're going to say that the label on vertex B is going to be given the minimum of what it was before. What was it before? You just look up to the previous step. It was infinity. What is it? The next piece? Well, the next piece says take the label of the newest member. The newest member was the source, A. So this is T of A right now. So T of A was 0, and we add the weight of that edge, the edge that goes from our vertex. This vertex V is vertex B, and vertex W was vertex A, so that's 3, that edge weight. So we're just taking the minimum between infinity and 3. Clearly the minimum is 3 in this case. All right, so now what we've done is we have just relabeled the vertex B with a label of 3 instead of infinity. Okay, now we're not done because step number 3 says to do this for all of the neighbors that are not yet in the solution set. So we've done it for B, and now let's take a look at C. So T of C will be equal to the minimum. Maybe I'll write it out a little bit more carefully. This is the minimum of what T of C used to be, or what T of A was, together with the distance, the edge distance from A to C. So AC, like that. So really this is the same thing, but I've just written it out specifically. And that's the minimum of, what did it used to be? It used to be infinity. What's T of A? That was 0. And what was the edge weight for AC? It was 1. So let me move this piece down a little bit more. Okay. So it was 1, and now we take the minimum, and we're going to definitely see that we get 1. So now we have given B a new label of 3 and C a new label of 1. And similarly, we'll take the label for D, and again, this is going to be just the minimum between what it used to be, infinity, and the label of A, together with the edge weight of that edge, that's 2. Okay, so the minimum of infinity and 2 is clearly 2. So what we've done is we've just changed T of B, we changed T of C, and we changed T of D, but T of E and F are still set to infinity. So now we've just completed step number 3 for the latest member. What does it say to do next? Well, step 4 says to pick any vertex that's not yet in the solution set, which has a minimum label. And we're going to add that to S. So let's go back down here. Right now, the only vertex that's in the set S was A. So we're going to add a new vertex into that set S, and it's going to have a minimum label. So let's take a look at all the labels we have. It's not going to be E or F because they're still at infinity, so it's just between B, C, and D. And it's clear that the minimum among those is T of C. So what we'll do now is we will add, that was step 4 really, we're going to add C to S. So now S looks like this. It's A as well as C. Okay, we have to now repeat step 3, but our W vertex, the newest member, is now vertex C. So we look over here, and we're looking from here at the neighbors of C, which are not yet in the solution. So A was already in the solution, and these are the only 2 neighbors left of C, which are not. Okay, so now I'm going to say that I think we can easily figure this part out ourselves. Again, we've done it enough times that we know what it is. So I'll just erase this part that we don't need. And we're going to repeat step number 3, but now our new vertex is C. So here we go. We're going to go into step number 3 again, but I'll use a different color. Our latest vertex was vertex C, so we're looking at all of the vertices in the neighborhood there, which are not yet in the solution set. So that's E and F. And we're going to try to relabel those. So the new label of E is going to be equal to the minimum of what the label of E used to be, which was always infinity up until now. So that was infinity. And the other piece is the label of T of W. What is W? It's the latest vertex. That's C. Plus the edge weight of C to E. So what is that? It's taking the minimum between infinity, or what was T of C? Well, we had it here. It was 1. T of C was 1, and so this is 1 plus the edge weight here, 1 plus 4. In other words, we give it a new label of 5. So E is now labeled 5. Okay, and finally, we're going to take T of F, and we should be able to see that it will be between the minimum between infinity, what this label used to be, and the label of 1, which got us to C, plus this next label, which gets us to F. So that's the minimum between infinity and 3, and so we get 3. So really I'm just doing this step again for vertex F, and I get the answer is 3 for this. Okay, now I have to do step 4 again. Step 4 says to look at all of the vertices which are not yet in the solution, and that's everything except for A and C, and look at one of the minimum values. So right now the vertex with minimum label is vertex D, and that has label 2, but it's not yet in the set S. So what we'll do now is we will add D to S. And now S is equal to the set A, C, and D. So each of these have been solved, and in fact maybe I will just highlight them in red when they're completely solved. We know that T of A is 0 and it's in the set S, so it's done. We also know that T of C is 1 and it's done. And then we know that T of D is 2 and it's also done. Okay, so what we're going to do is repeat step 3 with the latest vertex being D. If we look at that, I'll maybe use a different color again, so I'll use green now. If we look at vertex D and we look at its neighbors, which are not yet in the solution set, well, A was already in the solution set, so the only one left is to take a look at the vertex E. What we do is we're repeating step 3 again now, but our W vertex is D, and so we only have one vertex to look at, and it's the label of E. Well, that's going to be equal to the minimum of what E used to be labeled with, that's T of E, together with the minimum between that and T of the previous one that was added, that's D, plus the label of that edge, the DE edge. Okay, so what do we get? We get the minimum between what it used to be, which was 5, that was right here, that's what it was labeled with. Originally it was labeled with infinity, but then we changed it to 5. Now we're checking if it can be reduced anymore. So it's 5 together with what was T of D? Well, T of D was 2. And what's the edge label of DE? It's 1. So what's the minimum between 5 and 3? Clearly it's 3. So this gives us a new label of E, which is better than what we had before. And in fact, that makes sense because what we've done through this algorithm is we said, well, we can get to vertex E via this path, and that was the 5 we had. And now the algorithm has just shown us a better way to do it, which is going this way, which gives us a label of 3. So we're at the point now where we've finished off with that vertex D and all of its neighbors, which were not yet solved. And really there are only 2 more vertices in this entire graph that need to be considered. Those are B and F. Well, technically E needs to be put into the set S as well. But from now on, nothing is going to change. We're just going to go through and see what happens if we just follow the algorithm blindly. So let's see. We just did step 3 and it said it changed the label of vertex E. Now we have to go and look at a vertex which has a minimum label and add that to S. Now both vertex B and vertex E have minimum label 3, so it doesn't matter which one we choose. We can choose either. So in this case I'll just say let's add B to S. It doesn't matter, I could have added E as well. So now S is the set A, C, D, and then B. And if you look at B being the latest vertex, step 3 would tell you to take a look at B and look at any of its neighbors which are not yet in the solution set, but it doesn't have any. So we're already done, there's no change. So there's no change. What I mean by that is if you go back to step 3, nothing happens, so you continue to step 4. And you again want to add a vertex which has minimum label, and that one could be considered now as vertex E because it also has a label of 3. So add E to the set S, and now S is equal to A, C, D, B, E, and again, if you look at E, its neighbors are C and D, but C and D have already been solved. They're already in the solution set, so there's nothing to do when you go to step 3, so there's no change again. And then finally, what you have to do is add the vertex F. There are no more vertices left to add, and we get S is the set A, C, D, B, E, F, and again, there's no change. So what we've got now is all of the vertices are now in the solution, and we can just read off their labels. So what are their labels? A still has a label of 0, that never changed. C started with a label of infinity, then it got changed to 1, and it never got reduced after that. So it has label 1. D started off at infinity and then quickly got changed to 2, and that was it. Whereas B started off at infinity, changed to 3, and again never changed after that. E was the one that changed a little bit. It started at infinity, then it got changed to a value of 5 when we did this part of the algorithm, and then later on it got changed to a value of 3. So it still stays at 3. And then finally F, where's F? F has had a label of infinity, and then it got changed over here to a label of 3. So we tack that on as a 3. So what this says is these are the minimum weight paths from vertex A to each of the other vertices in the graph. And if you look at the graph again, you'll see that this is in fact the case.